Observe the response of the two cantilever beams which are of equal length and which have nearly equal major axis flexural rigidities. The one on the left has a high minor axis stiffness, whilst the one on the right has a low minor axis stiffness. Initially, as equal load is applied to each beam, their behaviours are almost identical. However, for the beam with low minor axis stiffness, as loading progresses, instability intervenes. The cantilever on the left does not suffer any instability and would eventually fail by plastic action. Lateral torsional buckling is only likely when a section has significantly different values of second moment of area and is subjected to bending in the stronger plane. So far, little has been said about the end conditions of the beams. As with columns, the end conditions have a considerable influence on the stability of the member. This support is fully fixed and restrains all component distortions, whilst the one on the right is a simple support which permits rotations in both the vertical and the horizontal planes. This test shows two slender beams of identical cross-section. One is a cantilever. The second is twice as long and is tested as a simply supported beam. Load is applied to the cantilever and failure is due to instability. The simply supported beam is also loaded. Again, failure occurs due to instability. It can be seen that the distorted, buckled shape of the cantilever is approximately the same as either half length of the simply supported beam. Viewed from above, the out-of-plane deflections of the cantilever and either half length of the simply supported beam are obviously similar. This is analogous to the comparison between a pin-ended strut, corresponding to the simply supported beam, and a cantilever strut, corresponding to the cantilever. This correspondence is not exact, as the behaviour of beams is more complex, as it also involves torsional effects. The end restraint provided to a beam has a major influence on the occurrence of instability, and can be utilised to enhance the load carrying capacity whenever instability is likely to occur. An alternative way of increasing load carrying capacity is via the provision of bracing. Consider again a slender, simply supported beam. If it were unbraced, it would fail by instability, with buckling occurring over the total length of the beam. Bracing is introduced at the third points and attached to stiff framing. This bracing is in the form of light, flexible wires. Load is applied and, relative to the unbraced beam, the carrying capacity is considerably enhanced, as buckling can now only occur between braced points. On plan, the elastic horizontal distortions show that the effective length of the beam is reduced to 1/3 of its overall length. For example, the shape of the middle third is the same as the buckled shape for an unbraced, simply supported beam. This results in a corresponding increase in the critical moment. In this example, although the bracing is very light, it has considerable axial stiffness.